Our next speaker is Peter Norvig. Peter is a research director at Google. He's been a real pioneer in this field, and previously he was at Sun Microsystems for a time. He was also at NASA Ames for a time. And if he's connected, over to you.
Okay. Thanks, Bill, and thanks, Rob. So you've heard a little bit about the excitement of what's going on now with machine learning, and particularly with deep learning, and you're going to hear some more from some of the other speakers. I want to step back a bit and say, how does this change the rest of the world? So we're all excited from the inside about machine learning, but what about the rest of society, and particularly the rest of the software industry? So software industry is 3% of GDP in the United States. If machine learning is going to change the way we interact with machines, we better figure out how that's going to happen. So let's just quickly review what is it that traditional software does. Well, we have a programmer or a team of programmers who come up with some idea, and then they very carefully write down instructions for, in this case, do that, in this other case, do that, just by thinking about the problem, and now we have something that supposedly works. And this makes software basically a mathematical science. When we're trying to get our programs to work, we theoretically know we could prove them correct. We usually don't go to all the mathematical effort because that's difficult. But we know that's the direction we're thinking about. We're using discrete mathematics to say we're creating this model or this piece of software that reflects what we want to do in the world. Now, in machine learning, it's the machine, it's the computer that's going to write the program rather than a human. But there's still a human in the loop who's now playing the role of a teacher rather than writing down all the steps one by one. And then there's an important role played by the data. So the teacher is teaching the machine how to solve the problem by showing it examples, and then the computer writes the program, but the program doesn't look like code that a traditional programmer writes. Rather, it looks like these deep networks, which are more or less black boxes. As Rob said, it's hard to understand what's going on the inside, and so all machine learning models are something like that, and then the deep learning models just have multiple black boxes connected to each other. So we've changed from a mathematical science where we can kind of look at each step and say, is that step right, to an empirical science. So we're now, rather than making it up as we go, we're observing the world, using data, and analyzing what's going on in the world. We're dealing now with probability rather than logic and discrete mathematics. And so there's a new set of skills. Another way to look at it is we could say programming was micromanaging. That we were saying, step by step, here's what you have to do. And now we changed it to teaching, where we're just going to show the computer what to do rather than tell it what to do. And I think General Patton put that very nicely. He says, if you don't tell people how to do things, but rather tell them what to accomplish, say, soldier, go take that hill, but you figure out how to do it, then they can surprise you with the results. And sometimes the surprises are proud ones. We can recognize that slug and tell it from a cucumber. And sometimes they're shocking ones where we get the wrong thing out and then we have to go back to the drawing board and do it again, right? So there's really two benefits to machine learning. One is it can do things that I or anyone as a programmer couldn't do. So as a human, I can recognize the difference between a slug and a cucumber, but as a programmer, I couldn't write that down because I can only do it unconsciously, not consciously. There's lots of tasks I can do both. Those are amenable to traditional programming, but the ones that are subconscious only, we can do through learning. We can't do it all through traditional programming. So it's opening up whole new areas. In addition to opening those up, it also just allows us to go faster. And we can talk about the speed up in things like speech recognition, which we could do by traditional programming, but progress just gets much faster when we apply these deep learning methods. So that's great. We have those two advantages, but When you go faster, sometimes problems happen. So I'm going to talk about some of the challenges and pitfalls. So lack of clear abstraction barriers, that a traditional program has components and we can analyze each component. When something has gone wrong, we can start doing a search through the components and we can say, I know the bug must be right there because all the inputs coming into there are good and the outputs are coming out of there are bad. Therefore, the bug must lie somewhere within this box. We can do that for traditional software. For deep learning, it's very difficult to do that because every parameter affects every other parameter and there is no localized piece. And similarly, the debuggability and explainability is hard. We can show it more examples and try to fix what it's doing, but we can't just go in and change one thing very easily. And in general, there's this lack of tooling. So here's an aid to programming that I'm old enough to have used. Today we have a whole new tool set, but because this is a big part of our GDP, there's a huge tool set that's been built up over the decades. But for learning, we don't have that tool set yet. We don't have the aids for the programmers or the machine learning researchers to do their jobs, and it's going to take years to build that up. Then there's a problem we call non-stationarity, which is really the sands of time. So if you train a system based on data, and that data accurately reflects the world, chances are you're going to get a good system. But if the world changes, now you're in trouble. You've trained it on data that's no longer relevant, the world has changed out from underneath you, now you have to update the system, and it's not always clear how to make that work properly. There's a problem of feedback loops. So here's one of the issues we face at Google, is we try to come up with the best results for any query and show them, and then we observe a user clicking on one of the results, and we can use that as feedback to say, oh, maybe they didn't click on the first result, they clicked on the second result. Does that mean that that result should be moved up? So we can gain from our observations of the world, but now we're not just observing, we're actually participating. And so there's a game between us, our users, the website designers, and we aren't a scientist off to the side. We're a participant that's changing what's happening, and our models have to reflect that. You get this kind of back and forth of the world changes as you change, and you take one action, and they take one action, and the models have to be updated continuously to make up for that. There's the issue of safe exploration. So we mentioned Go playing, and we might hear more about that. So that was a great breakthrough for machine learning. And one of the reasons we can make that breakthrough is that it's very easy to play millions and millions of games of Go against yourself without hurting anybody. And you can learn from that and improve. But if we want to build safe self-driving cars, we can do some stuff in simulation, but other things you actually have to do out in the real world because we don't have a perfect model of the real world the way we have a perfect model of the Go board. And when you're out in the real world, you can't just try everything, right? In the Go game, you can say, let's do something completely wild. Oops, I lost the game. That's okay. I learned something. You can't do that in the real world. So you're limited, and learning becomes much slower because you have to be safe. It's an issue we call transfer learning, which says you learn one place, and then you have to apply that someplace else. So here's a city, and if I train my self-driving car on one half of that city, either the near half or the far half, it's probably going to perform very differently than if I then go over that border and try to train it on the other half. And we don't have enough data to train. There's lots and lots of data out there, but we can't train everything all the time. So we have to be able to have our models be flexible enough that you train one place, transfer that over to another, and the theory to do that is just being developed. There's issues around privacy and security. If we're now dealing with data as an important part of what we do, we have to be good stewards for that. We have to protect the data that belongs to individuals. It's a question of fairness. So here's an example. Say I'm working on my speech recognizer and I'm at 93% accuracy and I want to get it up to 95%. And I have an idea. I say, I can separate all our users out into groups based on some feature of the way they sound, something in their vocal tract or their accent or something. And I can say, I can make one of those groups individually better without helping the other groups by applying some engineering effort to them. Now, if I want to do that, and I want to get up to 95%, what group am I going to pick first? Well, if I pick the largest group, then that's going to bring my overall score up the most. If I pick a small group, it's not going to bring my score up that much, my overall score, because there aren't many people in that group. And so without having any notion of prejudice, I've now reinforced this tyranny of the majority to say, if my goal is to have overall success for everybody, then what I end up doing is spending more effort helping the majority, whatever that majority may be. It's not necessarily race or gender or anything else. It may be something very technical about the way their vocal tract is built. But in all cases, I'm going to be encouraged to work on the majority rather than the minority. And if I think that's not fair, then I have to change my rules. I have to say, I'm no longer trying to get the best average score over all people. Maybe I'm trying to get the best average score over these groups rather than over individuals. And so I have to decide what I want in order to get the right results. And in general, that's a big question. What is it that I want? So we've gone from saying we're going to program computers by telling them what to do step by step to saying we're going to show them examples and then tell them to given those examples, optimize what we want. In order to do that, we have to know what we want. And that can be difficult. Now, I'm going to refer to two important philosophers in this field. And I have to say here, I'm going to go with the Nobel laureate, that I think Mick has it wrong, right? So he says you can't always get what you want, you get what you need. I think that's not true. I think we get what we want. Maybe not everybody individually, but as a society we get what we want because we create these marketplaces and we tell the market collectively what it is what we want, and the marketplace responds to that. So we've built systems that are specifically designed to give us what we want. The problem is we're not very good sometimes at really articulating what we want or really following through for what we truly want, right? So these are the things that we need, but when we participate in our marketplaces, this is what we end up saying that we want. And so this is what we're given, right? So you download Angry Birds and you play it for 100 hours, and that means there's 100 recommendations to other people so that they're going to be recommended and they're going to play it. And at the end, you all smack your head and said, I wish I had all that time back. But it's too late because you've already acted in the marketplace and you've made your choices. So these are the types of issues we're looking at. We're trying to answer all of them. It's a new science of how we do programming and how we do learning. And we're going to have to tool up to make that better and give ourselves better tools to be able to answer these questions. I have some time now for... Okay.
Good. Surely that will engender some questions. Please go to a microphone if you have a question.
You spoke about safe exploration, but when I think of the control engineers, and this is an old, mature field, control engineering, and they had to do safe exploration with chemical plants, nuclear plants. Why is this different?
Right. So that's a great question, and that's the kind of methodology we want to use, but we're applying it to different types of models, right? So Bill said in the introduction, I worked at NASA for a time, and so part of what I would be to go to flight engineers and say, we have this new technology, do you want to use it? And they say, well, wait a minute, you got all this software, and you've got not just straight line. We know how to analyze linear systems, but you've got a conditional inside a loop. How do we analyze that? We can't do that with the math we have. We're worried we'll get into a state that we don't understand. So that's the problem. We have the methodology, and people have looked at this very carefully, but they shy away from models of the complexity that we're dealing with now because their analytical tools aren't good enough.
Great. I'm not seeing other questions, so let's, yep. Could you go to the microphone? We're also webcasting this session, and we want people to hear the questions.
You've heard a lot about convergence research, and I think from a lot of what you said that you see a need for cognitive science and social scientists at Google to answer a lot of the questions you raised.
Yeah, so I think that's right, and I think we've been moving more and more in that direction as the problems go from not, can I write down the instructions without having bugs and turn that out quickly, to can I process this data to give me a system that the users really want? And in order to do that, we have to do more of understanding the users, understanding their interactions with us, as we saw in the vision research, understanding their physiology of how their eyes and brains work, and then also understanding the sociology of how they interact with each other. So there's a lot of openings for that.
Yes, I think a related question. I think that in science we go at the beginning thinking that things are fairly simple, then they get amazingly complicated. But out of that complexity, and you think that we could come up with simpler rules that give us an idea of how the machines learn. Just like we're trying to understand how a child learns. Right? If you try to analyze every neuron and see what it's firing, it's impossible to understand. But if you take it to a different level of complication, then maybe it's more practical. At a different scale, basically, you cannot zoom into that level to analyze this.
Right, that's a great question. And we'd like to understand better what's going on, and we have some tools to look inside what we're doing. I think there's two levels of understanding. One is, can we understand the machine learning models that we build? And we're working on that. And then secondly, you brought up this idea of then, can we then use that to understand how human learning works? I think that's a fascinating area. I like to keep the two separate because I think if you aim for two mountaintops simultaneously, you usually end up in the valley in between. So I'm saying, I'm doing engineering, other people can do neuroscience. It's great for us to talk to each other and be inspired by each other. Let's not try to do both simultaneously.
Question over here.
Thank you very much. A lot of what you were talking about seem to have inherently moral or political content. And I'm wondering what kind of expertise you are bringing to bear. So, for instance, when you're speaking about choosing particular groups in order to include in your learning, or choosing the appropriate goal to aim for, so improving diversity as opposed to improving your KPI for answers or whatever. So what expertise do you bring to bear on that? Are you using political scientists, ethicists, and so on and so forth?
Right. So I think that's certainly true. I think all these issues are coming out. They were always there all along, even when we were doing traditional programming, but I think they were noticed less because it was sort of these ethical decisions were farmed out to the individual programmer where, as they wrote a line of code, they thought about it and tried to do the right thing. Now that we know that the machine learning systems by themselves don't have any ethics, we have to now bring that to bear, right? So basically we just hire teams to work on those types of problems, and we have review boards and committees and so on, and sets of standards, and we try to do the best we can to make the whole process better rather than to distribute the decisions out to individuals.
One of the things I've thought about for a long time, and your wonderful picture of what we need versus what we want reminds me, and that is that there are things that affect lots of people a very little bit, and therefore
I wonder if that's somehow something you can integrate into your assessment of what you want.
Yeah, thank you. Yeah. Yes, so I think that's certainly true, that there is this notion of you take away a little second of somebody's attention or something like that, and now they paid a price, but that doesn't always get logged. So I think we do have to pay attention to those types of things.
Yeah, I probably could give you an example from copyright and course tax 20 years ago. That affected lots of students. The price that copyright owners were asking affected a lot of students. They were actually the decision makers, those were the professors, and they were going to be gone within 4 years.
Mm-hmm.
So they weren't going to organize themselves and say, you've got to give us a fair price.
Right.
But there was sort of no way with the market to get that information to the copyright owner.
Okay, let's thank Peter again.